Pre-Calc section 3.3 is on finding the zeros of polynomial functions. Now if you recall back to section 3.2, which was just yesterday, we were looking at polynomial functions of higher degrees. And at the end of it, we found a little bit to do with the zeros of it, and we're trying to graph those. This is going to give us a little bit better handle on how to find those zeros, especially when they don't factor so easily. Okay? So the first thing we run into is what's called the rational zero test. Okay, a rational root theorem. We call it, in other books we call it the rational root theorem. This one calls it the rational zero theorem. Again, roots and zeros, same thing. Basically it says if I just have any polynomial, and if it's not easily factorable, okay, that's always the first thing you want to check to see if you can factor it. If it has integer coefficients, in other words, these have to be all of these have to be integers. They can't be fractions or decimals. If they are, we have to multiply by a common denominator and get rid of the fractions. Okay, if they have integer coefficients, and P over Q is a rational zero. Now when it says P over Q, what they're talking about, this back here is your P, and this A is your Q. Okay, so the constant is P, your leading coefficient of the leading term is Q. Okay, so, and P over Q is a rational zero in simplest form of P, then P is a factor of the constant term, and Q is a factor of the leading coefficient. Okay, what they're trying to say here, and it's a lot of gibberish, we're going to find the rational zeros, all possible rational zeros, by making a fraction of the last term over the first term and all their factors. So I've got to get all the factors of those and make all possible fractions of those factors, positive and negative, and that will give me all possible real x-intercepts. Okay? So a little bit of a tedious process here, but it's not a super hard section. First of all, I got a few examples here. So P of x, we have this function. They want us to find the zeros and state the multiplicity of it. Okay? So to find the zeros, again we factor it, we get into its factored form. We set each of the factors then equal to 0. Solve it out. So I get plus or minus the square root of 3, negative 5, and negative 5. Now instead of stating the multiplicity of each, you just want to do it if it's more than once. So therefore we know x equals the square root of 3, negative square root of 3, and negative 5 twice, so we call that a double root. Okay, if it happened 3 times, I had 3 x plus 5s there, I'd call it a triple root or a TR. All right? So that's all we're doing now is we're trying to find the roots of this. In number 15, we're just going to take this in 2 steps. Okay, this whole rational root theorem. First thing wants us to list all the possible zeros of this function. So remembering that P is the last term and Q is the first term. All possible rational roots are given by the factors of P over the factors of Q. Now, the positive and negative value of P and Q doesn't matter because we're going to do all positive and negative values anyways. So it's the factors of 6 over the factors of 4. Factors of 4 are 1, 2, and 4. Factors of 6 are 1, 2, 3, and 6. So the possible zeros. The possible zeros of this polynomial. Possible rational zeros. Okay? Not imaginary. The possible zeros are given by plus or minus 1 over 1, positive and negative 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 2 over 1, 2 over 2, 2 over 3, 2 over 6, 4 over 1, 4 over 2, 4 over 3, and 4 over 6. Oops, there we go. So 1, 2, 3, 4, 12 doubled. There's 24 possible. It's the way I have it written right now. But if you look, we can simplify these. This is 1, this is 1. I don't have to write it more than once, so I don't have to worry about that number. Okay? Any other 1/2s in here? Well, I don't see any other 1/2s, so we're going to have to do that. Any other 1/3s? I don't see any other 1/3s or 1/6. How about 2s? Well, 4 over 2 is 2, so we don't have to worry about that one anymore. 2/3, well, 4/6 is 2/3. 2/6 is 1/3. So I have it already up there. Okay? 4 and 4/3 I don't have other copies of. So now we just reduced it down a little bit. But so the possible zeros are positive and negative 1, positive and negative 2, positive negative 4, positive negative 1/2, 1/3, 1/6, 2/3, and 4/3. Now you ask, okay, what does that do for us? Well, if we go back to section 3.1 where we learned synthetic division, we know how to find out if something's a root or not. We do synthetic division with it and hope that I get a remainder of 0. So here we go. This is number 51, which asks us to basically do the whole thing all at once. Okay, so it's the only example I'm going to do because they all build up to this. First of all, it wants us to find all the zeros of this function. So to do that, I take my p over q. Now, if I could divide this function by a constant, if all of these were even, I would definitely do it. Okay, because that would simplify it, hopefully make it a little bit easier to work with. I'm just right now checking my 51 to make sure I've got it copied down right. Minus 2 plus 27 minus 12. We should be good to go. So p is 12, q is 2. Factors of 12, 1, 2, 3, 4, 6, and 12. Factors of 2, 1 and 2. So my possible factors are plus or minus 1 over 1, 1/2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 4 over 1, okay, so we've got those. Let's get rid of the ones that are the same thing. 1 over 1 is 1. I don't think I have any other 1s in here. 2 is 4 over 2. Oh, I do have another 1 there. 3 is 6 over 2. 3/2. Okay, 4. Okay, so let's simplify it again. So I've got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus and minus, 12 over 2 is 6, so I don't have to worry about that, plus or minus 12, 1/2, and 3/2. So there's everything I have to check. Okay? Now, here comes the fun part. Kind of tedious, but we'll get through it. We're going to try and find, now this is to the 4th power. Okay? So what I need to do is find 2 roots that work, 2 of these, which will drop this down to a quadratic. And then I can use the quadratic formula or factoring to solve the rest. So I don't have to go through this and find all 4 of them, but I do have to find at least 2 that work. Okay? The second thing is once I find one that works, it might be a double root, so I have to check it again. Keep checking it until it doesn't work. And always use the reduced polynomial to solve or to check with the other factors. So once I find one that works, this will come down to a quadratic or a cubic. Then I would use that cubic to keep checking. Okay? So we're going to look. I just have to pick something to check with. Well, 1's always a good one to start with. I do my synthetic division. I've got 2, -9, -2, 27, negative 12. Drop the 2 down, 1, negative 8, negative 8, negative 10, negative 10, 17, 17, 5. 1 did not work, so I don't have to worry about 1 anymore. Let's try negative 1. Negative 1, and I'm going to do my synthetic division again. 2 drops down, gives me 2, negative 7, 7, 5, negative 5, 22, negative 22, negative 34. So 1 and negative 1 didn't work. I don't have to worry about those anymore. Now I'll try 2. I know you guys in the video are watching this going, oh my gosh, this is going to just be terrible. 2 times 2 is 4, negative 5, negative 10, negative 12, negative 24, 3, and 6. That didn't work. Oops, that didn't work. So now I'm going to try negative 2. Imagine doing this without synthetic division, huh? 2 drops down, negative 4, negative 13, 26, 31, negative 62, negative 40, 80. Okay, that one's not going to work. Now you got to be careful when you're doing the synthetic division, because if you mess up, you might miss one of the factors. Okay, so I'm going to jump ahead. I don't think 3 is going to work here for some reason, so I'm going to go ahead and try 4. Two drops down, 8, negative 1, negative 4, negative 6, negative 24, 3, 12. There we go. So I know right now that 4 is a root. So I no longer use this one for my synthetic division. I use this answer because that's my simplified polynomial. Now I have to try 4 again because it might be a double root. So 2, 8, 7, 28, 22, and it's going to be too big. So I know 4 only works once. So I have to try negative 4. 2, negative 8, negative 9, 36, and it's going to get too big. So I know 4 is not working. So I need to try and get lucky here and see what else I might be able to use. Okay. Now if I take a look at the actual polynomial, 2x cubed minus x plus minus x squared plus 6x plus 3, I might be able to factor that. So I might be able to jump around and not do this. Let's find out real quick. I can factor an x squared out of that. 2x minus 1. I can factor a 3 out of this. But they're not the same. So that was kind of a waste of time. But I knew somebody would want to try it. One more time. I've got 2, negative 1, 6, and 3. Let's see. Let's try a fraction. Okay. One thing I don't do is I don't jump around and I can jump around and try different things, but I don't unless once I try one of them, I always try the other two. You know, the positive and negative. That way I don't have one of them sitting out there. So 2, that's 1, that's 0, that's 0, that's 6, that's 3. Oh, I made a mistake. Negative 6, that should be a negative 6. So that should be a negative 6. So that should be a negative 6. So 1/2 works. Now if I'd have gone back here, I would have been able to factor it. Okay, so I messed up recopying it, which would have been able to factor. Might have saved me a step. Luckily we caught it. So now I know 1/2 is one of the roots. And now I have 2x squared minus 6 equaling 0. Solve it out. And I have the other two roots. So the roots of this function look like that. 4, 1/2, and plus or minus the square root of 3. Okay, and that's all they're asking you to do is find the roots. Now you understand why the assignment is as short as it is. Each problem will take a little while, but once you get the process down, it's really not difficult. Okay, let you go.